Hey everyone, welcome. Go ahead and grab your magnifying glasses, because today we are all data detectives. We're going to be looking at raw data, which, let's be honest, usually just looks like a giant messy pile of numbers, and we're going to learn how to use two absolutely incredibly powerful analytical lenses to investigate data mysteries. By the end of this explainer, you're going to be able to look at a list of raw numbers and immediately know how to reveal its hidden story.
Here is our roadmap for this explainer. 1. Shaping the data. 2. Histograms, the wide lens. 3. Box plots, the X-ray. 4. The worked example. And finally, 5. Our recap and transfer question.
Section 1. Shaping the data. All right, let's dive right in. The fundamental idea of statistics is that variation is present in pretty much any set of data. But raw numbers alone, they kind of hide that variation. Graphing helps us actually see the shape of the data, and that shape tells us a story about where the numbers cluster together and just how spread out they are.
Now, before we even think about looking for patterns, we've got to state the absolute golden rule of statistics. Read it, memorize it, and seriously, never forget it. A relationship between two variables does not mean that one causes the other to occur. While we're going to be out there hunting for patterns, shapes, and correlations, correlation absolutely never proves causation. Two things might move together simply because they're both related to a third, totally hidden variable. You've always got to keep that in the back of your mind if you want to be a truly impartial data detective.
Okay, next up, let's knock out a quick piece of mathematical shorthand before we start using it. When you see the lowercase letter n, it just means the total number of data values in our sample. That's it. If you count the shoes in your closet and you have 10 pairs, well, your n is 10. Simple as that.
Section 2. Histograms, the wide lens. I want you to think of the histogram as your wide-angle lens. It steps back, zooms out, and looks at the overall landscape of the data.
So how is a histogram actually built? It consists of contiguous or adjoining boxes. We group our data into equal intervals along the horizontal axis, and the vertical axis gives us the frequency, basically how many data points fall into that specific interval. Now, a good rule of thumb is that histograms are really fantastic for larger datasets, like, say, 100 values or more. And because the bars are literally touching each other, this type of graph instantly reveals the overall shape of the distribution. It shows us these giant clusters where data bunches up and brilliantly highlights the gaps where data is totally absent. All right, time for a quick pause check. I want you to pause this explainer for just a second and put on your critical thinking cap. If you are specifically trying to spot gaps where absolutely no data exists, which graph is going to show that better, a traditional bar chart or a histogram? Hit pause, lock in your answer, and then hit play when you're ready. And the answer is histograms. This perfectly illustrates why those adjoining boxes matter so much. See, in a regular categorical bar chart, the spaces between the bars, that's just a design choice. But in a histogram, the numbers on the bottom flow continuously. So, if there's an empty space between two bars, it literally means the frequency is exactly 0 for that interval. It's a true, literal gap in your data landscape. Section 3. Box plots, the X-ray. So, if the histogram is a wide-angle photograph of the whole landscape, the box plot is like an X-ray. It strips away all the noisy surface details to show you the data's underlying skeletal structure. But before we go building one, let's define a little more notation so it's a total breeze when we see them in action. Q1 is the first quartile. You can think of it as the 25% mark of your data when it's all lined up from smallest to largest. Q3 is the third quartile, so that's the 75% mark. And the IQR, that's the interquartile range, which is simply Q3 minus Q1. It represents the literal mathematical distance that covers the exact middle half of your data. Now, a box plot is actually built entirely from just these 5 numbers, cleverly called the 5-number summary. You find the absolute lowest value, your Q1 mark, the median exactly in the middle, your Q3 mark, and finally, the absolute highest value. By slicing the data perfectly into quarters like this, each section of a box plot ends up holding exactly 25% of your data points, no matter how weird or stretched out that section might look visually. So the real superpower of a box plot is how it shows concentration. The box itself captures the middle 50% of your data. The whiskers extend out to your minimum and maximum values. But here's where it gets cool. If there is an extreme outlier, a number that's just wildly far away from the rest of the pack, box plots will often explicitly mark it with a little dot, rather than stretching that whisker all the way out. Because it uses quartiles and the median, it is absolutely ideal for handling highly skewed, lopsided data. Putting them head to head, our two lenses serve very different purposes. The histogram shows you the mountains and the valleys, right? The clusters and the gaps. The box plot, on the other hand, shows you the dense core, the true center, the spread, and any extreme outliers hiding on the fringes. Section 4, the worked example. Okay, let's actually put these tools to the test with a real-world example. Take a look at this raw data set. A researcher went and asked an 8th grade algebra class how many hours they spent playing video games over the weekend. We've got 25 data points here, so our n equals 25. Now, just staring at this wall of numbers, it's pretty hard to tell what a typical weekend looks like, isn't it? Let's grab that wide-angle lens first, the histogram. If we group the data into intervals of 8 hours, here's what we get. From 0 to 8 hours, we have a frequency of 4 students. From 8 to 16 hours, 6 students. But check out that 16 to 24 hours block. We have a massive frequency of 15 students clustered right there. This histogram instantly reveals that the overall shape of our data is heavily skewed to the left. The vast majority of our data is bunched up on the much higher end of the scale. Now, let's swap over to our X-ray lens, the box plot's 5-number summary. Our minimum is 0 hours. Q1 sits right at 10 hours. The median, our true 50% mark, is 17.5 hours. Q3 is 21.9 hours, and the absolute maximum is 24 hours. The IQR, that middle 50% of all the students, falls entirely between 10 and 21.9 hours. The spread is super clear here. Time for our second pause check. We just saw that the video game data was heavily bunched up on the right and severely skewed. So when dealing with highly lopsided, skewed data like this, which graphical lens gives us a better, more reliable measure of the true center and spread? Go ahead, pause the explainer, think about it, and resume when you're ready. The answer is box plots, and here's why. Since box plots rely on the median and the IQR, they are highly resistant to being dragged around by extreme values. Say one student played exactly 0 hours. It definitely stretches that bottom whisker way out, but it barely nudges that median center point at all. The box plot keeps us firmly anchored to the true core of the data. Finally, Section 5, Recap and Transfer Question. We have covered a ton of ground today, data detectives. Let's lock in this knowledge and test your skills one last time. Here is your ultimate summary. N, Q1, Q3, and the IQR. That's your mathematical shorthand. Histograms are your wide lens, showing you the big picture landscape, the clusters, and those literal zero-frequency gaps. Box plots are your X-ray lens, revealing the structural skeleton, the middle 50% concentration, the median center, and those wacky extreme outliers. And above all else, please remember that just because two things graph nicely together, correlation absolutely does not equal causation. And I'm going to leave you with this final, provocative transfer question to take out into the real world. Imagine for a second you are a shoe manufacturer, and you have to decide exactly which shoe sizes to produce in bulk for your next big release. Would you rather look at a histogram of population foot sizes or a box plot? Which lens is going to give you the actionable clusters you actually need, and which one might just hide them inside a box? Think about it. Thank you so much for joining me on this explainer. Keep asking great questions, and happy data hunting.